All right, let's go ahead and implement it. By the way, everyone please full screen your PuTTY terminal or whatever terminal you're using so we can get at least all the real estate over here. E-size pane, okay, sure. We're on lab 23, by the way. Either 24 or 25, I don't know which. Oh, who's doing this?
Sorry. I'm trying not to.
It's not working? All right. By the way, what just happened when I typed that in? Did any of y'all's terminals produce a...
Yeah.
Allocating size to something.
Y'all have a PDF on yours?
Nope.
No, I didn't think so. Too bad. All right, so look at my screen.
I'm offended.
Well, I'm offended that you're offended. Okay, who closed it?
I don't know how to process that, but I'm upset.
Enjoy it.
I don't know how to process that, but I'm upset.
But you're upset? Oh, okay.
Type show it.
Oh my goodness. There we go. All right, now we're good. So now you can play with this all you want. There we go. Anyways, so this should hopefully look very similar to your last lab, except for instead of graph AN, it's graph AL for adjacency list instead of adjacency matrix. So you're going to implement all the same things, but now with adjacency list. Create an empty graph. This is going to be a lot easier with the adjacency list. Graph with the number of vertices, be able to deallocate it, be able to add some vertices to the end. Notice I'm passing in the number of vertices I want you to add. The graph always starts at 0, and you just append more numbers towards the end. You can remove a vertex. Notice that once you remove it, you need to update all the edges that are affected. Keep that in mind. I think that's where people are having problems with this last lab. Remove vertices. Remove vertex, add an edge. You got to start and end. Remove an edge from a graph. We have depth first traversal, breadth first traversal, which we talked about last time. We'll go at least an example there. Need to know if two things are adjacent. And then lastly, we will run Prim's minimum spanning tree algorithm. We will talk about that soon after this lab. Of course, you always want to be able to print out your graph. All right. Any questions about what you need to accomplish before we start doing this as a class? No? Okay, great. All right. So, thanks. All right, come on, guys. Everyone full screen. We still got some empty.
How can you tell when it's full screen?
Just make the window big. Oh, there you go. Someone did it.
Oh, okay.
Yeah. Well, the problem is if the one person who hasn't done it affects everyone else. You it's not my fault. All right, so yay, we can compile. Let's go ahead and take a look at source graph HPP. Here we go. Hey, look, I included vector and list. Hopefully that helps you out.
So nice.
I am. All right, class to begin filling out. This is an adjacency list, so what do you think the data structure should be? A vector of list. All right. Have at it. And remember, the list is templated, so you got to have it be a list of something. Well played, sir. Well played.
Wait, can we list the pairs for this?
Yeah, we can just use pair. Well, W, a list of weights. How will you know what the destination is? You don't. So that is not useful.
What's
I like
the
this, I like
asymmetrical
this.
distance?
It would be node, right?
Try STD pair. And then you can make it, the destination is always an integer, so make it an int comma weight. All right, and then there we go. Wow, look at that. Thank you for putting those spaces in case we're using archaic C++ compilers. All right, what are we calling it? Some name. Yeah, let's call it something better. Start with M. All right, nice, well played. I see how this class is going to go. The thing, oh no, the thingy. You got to put the Y in there, man. All right, come on. M. M. Oh my goodness. All right. All right, so we're doing graph, M graph. There we go. Perfect. I gave you the answer. Wow.
Awesome.
Hold up, let me go cap that. Put that on loop.
On loop.
Yay!
All right. I actually can't read that on the screen. It's a good thing you can look at it here. AK thing 2. All right, I'm good with that.
Alright.
All right, so we're going to escape. We're going to compile. Let's see if that actually works. Oh, good, it does. So tab new. Let's open up the CPP. Hey, I've already written some of these out. So do we need to do anything in the default constructor?
Kind of. Should we initialize?
You want to initialize it just in case they
Things
try
to know.
something?
Well, it's kind of automatically initialized, isn't
Yeah,
it?
it's not using the stack.
Well, it's not on the stack. Well, it's on the same.
Initialize.
It's on the same memory space as the object itself. So it's either on the stack or the heap, depending.
Although the private variables aren't initialized in the same sense. Like they aren't set equal to a vector or anything like that.
Well, let's go look at this real quick. Where does mgraph reside?
Stack.
I guess it's in the same space as that, but it's.
Yeah, it's the same space as the object itself.
So when the object is created, this is also created, I guess.
Yes. So by creating the object, you automatically call the constructor for mgraph.
Okay. So
Yeah, it's kinda weird.
It's a point.
You could think of it as a pointer, which may be more helpful. You want to do it as a pointer?
No.
Keep it.
Yeah.
All right.
I know better.
You know better? Wow. Okay. But if we have a number of vertices, whoops, what do we need to do?
You got
Yeah, keep looking at your screen, guys. You don't have to look at mine. Wow.
I guess for each vertex we need to add the value
Wow.
to vector, add the list to vector.
You're gonna
Ye-
get the current vector size.
Yeah, we got to resize the vector.
So you just
Now,
need to-
I'm going to stop here because you probably want to call dot resize on a vector. That is going to have not happy results because vectors are weird.
You're adding them on the back, just open
Whoops.
the back, right?
Well, you want to use the constructor of vector. Hey, wow, that's cute. That's not what I wanted. I want to go over here. Oh, wow, it loaded fast for once. So the constructor for vector.
You cursed it, by the way.
Hmm?
You cursed it by saying that.
Oh, you're gonna.
Yeah, so you want to pass it to the vector. Wow, I completely forgot how you do that. Let me go look at my other code. It's weird. Oh my goodness. Oh, we didn't do it here.
No.
No.
It's elsewhere, but I forget which one.
All right, so we are going to make it a pointer.
Oh yeah. Because if you want to construct a new one.
Yeah, let's go ahead and do it. Let's just make it a pointer. So now we can just up here have mgraph equal new. Oh boy, that's a lot of typing. There we go, Mickey thingy 2. And then down here we'll go ahead and pass in the vertices. Vertices. Alright, I wonder if that compiles.
What would the point of this function be? If we don't know the vertices themselves, why would we just want the size of them? The number
So,
of vertices?
keep in mind that we're working off the assumption that all our graphs are going to be, the nodes are going to be starting at 0 and incrementing sequentially. That's it. And this is actually a very common way to do it because it keeps things simple. If you want to associate, like 0 is Charleston, 1 is Paris, 2 is whatever, you just create a separate hash table and map 0 to Charleston, 1 to Paris, so forth and so on, if you need to know it. But by keeping them integers, it it simplifies a lot of our coding.
So, but if it was, if we just created an empty vector and then pushed to it one by one the vertices which we wanted, would that?
Oh, I see what you're trying to say. It's a vector of pairs. Well, you can't push the vertex because what is the vector actually composed of?
It's composed of a linked list.
A linked list. So you can't push an integer. You can't do that. But all this is doing here is allocating whatever we're passing in as vertices, that number of linked lists, empty linked lists.
Mhm.
But we're automatically allocating all those linked lists inside of the vector.
So then I guess we can change the value of a vertex without.
No, you don't change the value of vertex.
I see, yeah,
Yeah, yeah.
I see now.
Okay, great. Yes.
So I guess one way we could have solved that is just make it a pointer inside the vector rather than an actual list inside, and then you could just push null every time for that amount of time.
You could. Who wants to be pushing null?
That's fine. I just was confused.
All right, good. All right, good talk. All right, let's see if that compiles. Oh, it's already compiled. Well, let me go look at what our main function does. Hey, look at that. Creates 100 of them. Did it actually compile? Let's see, make the graph. Oh, it even ran it in segfault. Well, that's a good start. Okay, so supposedly that worked. One of the best things you can do is when you create you can at least implement the print function. How will we implement the print function? Oh yes, oh boy, the iterators. What? Take it from the hash map?
What C++ are you running?
Oh, here we go.
Because auto only works on C++. What is
Oh, you're gonna auto it. Wow.
It's in 14, is it? Versus 11.
Well, hold on. What is each element inside of graph? It's a list. So now you need another for loop.
Inside the list.
Oh, man, that's not good.
That's not good.
Or
I
you
mean,
can do the
it's
same auto
squared.
again.
What's that?
I mean, you could do auto again.
Yeah, just for auto it again. That'll work. If you want to see the auto syntax.
Whatever this is.
What is the?
All right, let's give it some better names.
This is the harder part.
Well, so the top one should be list because it's a vector of lists, and the bottom one should be pair. I would call it in list. Yeah, in list.
Guess I'll buy them.
How do you want?
Dot first. The first one's the destination. The second one is the weight. You probably need to put a open parentheses at the beginning. Man, this is great. Y'all get to type it. Okay, yeah, we can do it that way too. All right, don't forget to close your for loops and put an inline after that first for loop, or the inner for loop. Okay. All right, let me see if that works. Probably should call the function.
Yeah.
Let's not have 100. Let's have 10. Oh, that did not work. Oh yeah, in tmux you can't. I forgot how that was done.
What C++ is this running in the make file? Because if it's running anything under, I think, 11 or 14, it can't do auto.
Let's go ahead and let's do that real quick. Let's see if that makes the errors. Nope, we still get the novel. Oh yeah, so you're saying, hold on, make file. So which
I'd say C++ 14 would be the...
was it?
C++. Yeah, I think you have to put the plus.
Oh, that's right. C++ 14. I keep forgetting the syntax.
Yeah, I think 11 is
Nope.
no, it's still mad.
He doesn't like you. Alright, let's try something else. 4. Oh, great. Type name. Oh, here we go. What was it? Oh, I gotta type this whole thing out. List. What's that?
I just don't like looking at that.
Yeah.
Yeah, that makes me uneasy. Wow. I list does not equal mgraph.end. I list plus plus. Alright, let's see if that actually compiles. Oh, at least it's not as complicated. Oh, probably because graph is a pointer. Wow, sorry guys, I'm a lot faster.
You're slipping.
No, I'm really fast. I didn't let you read the error message. There we go. All right, so now we need to do the inner for loop. So this is I list, I pair. There we go. Huh. Oh, that was funny. It's still compiled. Wow. All right, no whammies. Oh, there we go.
No way.
No whammies.
Woo!
Woo, that was fun.
Yeah, let's do it again.
Let's do it again now. What?
Was it just 10 new lines? Or
Yeah, why is it 10 new lines? Yeah.
because we have 10, empty lists.
Right, right. We have 10 nodes and there's nothing connecting them.
Okay.
Yeah, so
I thought we didn't call it.
technically, so far it looks like the print function's working. Great.
Yeah.
Yeah, yeah. Let's go ahead and add an edge. That sounds like a good idea. So gal dot add edge. Where do we want to go from?
1 to 10.
1 to
Or
10.
1 to 9.
9, that's right. And what's going to be the weight?
50.
50? Alright, so
That's the
so normally that should print something out. But right now it's not printing anything because we haven't implemented it. Alright, how do we add it?
We go to the one, well, it's not first, but the one index of the vector of list.
Okay.
Add a pair to the list which goes to 10, and for the first value it pairs 10, second is 50.
Okay. Oh, I know if you'll actually know what you mean when you say it. What's that?
I don't.
You don't? Oh, maybe I should have you code this.
Everything's high level. So you can think about adding an edge as like adding a path, right?
Not a path, it's an edge. Remember, a path is a collection of edges. An edge is just one connection between two nodes.
Okay.
Mm-hmm. we go. Yeah, what if there's already an edge? Well, if someone didn't, delete the PDF, maybe it would have told you what to do in that case. So let me go. Just gonna throw that out there, but we'll not deleted it, but closed it. So let's
Okay.
yeah, y'all killed the process. Thanks, guys. Let's see if this tells you. Add edge, adjacency to the graph. Oh, it doesn't tell you. Oh, that's cute. I'll have to get back to you on that.
So does that mean we can do whatever we want?
Nope. All right, so we'll just have a return true. All right, let's see if that compiles. Nope.
Awesome.
And you can't see the top of it.
I think there needs to be a. Oh wait, what?
Oh yeah, I'm graph.
Oh, you're not in insert mode. Hold on, stop. Hold on, what did I just do? Ah! Now go ahead.
Okay.
Okay. Okay. All right. We'll see what that does. Non-pointer. Yeah, so you're on the right track. The issue is that mgraph is the pointer, not what comes from mgraph. So you got to dereference mgraph first. There we go. Y'all see what I did there? Yeah, because mgraph's a pointer to a vector, so you got to jump to the vector first, and then you can go to the element and go from there.
Can I just enhance the print function for a second?
Sure, go ahead. Enhance.
Just bothers me.
Okay.
Takes all the code just to delete it. It's already. Takes away all of it.
I.
I?
Hit I.
Okay. I mean, I guess.
Open curly bracket. You probably want the curly brackets.
Are you looking for putting the comma in there?
Oh, you want to know which one it is. Okay. Oh, okay. Yeah, that'll work. Like that?
Do we now get to fix what we didn't fix then?
All right, let's go see what that looks like.
All right.
That better? All right. All right, so we probably should add some more edges. What else would you like?
Let's do 19200.
Ooh. Let's not do that.
I want to fix that.
Oh, yeah, I was just about to say we didn't do anything. About it. So I think there are options either return false because there was already an edge or replace the edge.
Yes, and I would like to tell you that, but I'm recording my screen, so I can't go and find the documentation right now.
Oh.
So I will have to get back to you on that one real fast.
That's why we don't want to mess with it.
Yeah, that's why we're not messing with that yet. But let's add some other edges. So 0 to... All right, something else?
From 9 to 1.
9 to 1.
-50.
Negative. Let's stick with positive.
Okay.
We don't want to gain. We don't want to go back in time by going in through an edge. That'd be pretty cool, though. Yeah. 35. Any others?
3 to 0.
Sure.
57.
All right, guys. Let's just start adding some weird ones.
9001. Add a letter in there, see what it is.
Well, actually, I can add letters here, but you won't quite understand what it means. We can make it an L,
Yeah.
but let's not do that.
There's nothing make it
A long, yeah.
Take it down here.
All right, so there we go. Okay. Yeah, looks like that's working just fine. All right. All right. So we can add the edge, and now we want to probably remove it. Is that next? Remove, not the vertex, but remove edge. Okay. Of course, that returns if it was removed or not. So, how do we remove an edge?
Go check if there is anything at that vertex. Then we erase through until we find what we're looking for. It has to have the exact endpoint.
All right, so that doesn't sound like too much fun, but let's
If
Let's do
the
it
linked
anyways.
list that the start is ours,
All right, here we go. Sure, hang on. So yeah, we gotta go through the list. Let me go ahead and type this code out for you. It is a, what are we doing?
We'll do a for loop.
Let me steal this for loop down here. So it's going to be an iterator, but it's going to begin at mgraph sub start.
oh, what's the parentheses?
Yeah, the parentheses needs to be over here. Boom. And then while I pair does not equal mgraph sub, there we go. Start dot end.
But the, on the other one you have to start with
Oh yeah, that wouldn't be good. Yeah, let's fix that in a moment. Alright, let's see if that causes any errors. Looks like I may have typed that correctly. Let's go ahead and try and remove an edge. Wait, did I call it remove or delete? Remove, good. Which one are we going to remove? 3 to 4? There's no 2 to 4. Okay, 2 comma 4. Hey, no, so we didn't care about the. Well, let's go ahead and print it afterwards, of course. Okay.
So we need to say that if we
Now let's just make sure it compiled. Okay, good. It
if
didn't.
the first value of the pair was equal to end, then we, I guess, remove the pair from the list and return true, and then just leave it as it is.
I think it's called erase. I pair. No, because we're erasing from a linked list, not from a vector. I think it's erase. Let me see if I did that correctly. So, did we get rid of 2, 4? We did.
It's okay. Yeah.
Because I erased.
If it's erased and the I guess iterator.
Mhm.
Yeah.
Yeah, so I erased. The iterator is pointing to what needs to be erased, so we got it erased. Perfect. Otherwise, you return false. Good. Well, that was easy. All right, adding a vertice. What do y'all need to do? We're not going to implement it. I'm going to let y'all talk about it. Do what to the vector?
Push back with a new list.
Okay, push back. All right.
Oh, what is that? Oh, AMT is the amount of vertices.
Yeah.
Yeah, amount is the number of vertices to add. So if I pass 10, and your graph currently has 10 vertices, the new graph will have 20.
I mean, I would just I do 4.
Yeah.
I from 0 to less than mark. Just
Yeah, just push back AMT lists, AMT number of lists to mgraph, and then you're done. Yeah.
and you need a vertex because then you have to go to all of the edges and where the
Well, we're
edge
adding to the
points-
end.
I was talking about removing.
Oh yeah, removing.
Yeah, so like you have to go to all of the edges, and when they point to a vertex the value which is above the one you're removing has to subtract 1 from it. So
Yep.
it's 3K.
Yep, that's what you'd have to do. How about adjacent?
Well, go to the start. Basically, you can just copy the code from remove, but instead of removing, return the weight. If not, return it.
I'll just type it in. Return the weight. All right. Remove vertex. Oh yeah, this is gonna be a difficult one. Well,
Well, I would say we iterate through all of the lists first, and if there is an edge pointing to that vertex, we remove it.
Okay.
If the edge is pointing to something bigger, then we just subtract 1. Then we go and remove the edge.
right through entire graph, removing all edges that end with IDX. Good. Next, yeah, you update all edges that end with something greater than IDX. Oh, I'm sorry. You update all edges that end with by subtracting 1 from end. Okay, that's confusing. In other words, all edges that you, in other words, sorry, subtract 1 from all edges that end with a vertex greater than IDX. All right, great. So depth first traversal and breadth. Ooh, we didn't do breadth. So did I do breadth last time? I'm pretty sure I did.
We take one or the other.
I think we did breadth, so we should do depth this time.
Why is there 2 functions?
Yeah, why are there 2 functions? That's a good question.
We'll find out next time.
What was the function signature? Int node, okay. So what we have? gal.depth first traversal passing in print. Let's see if I typed that correctly. I did. Sweet. All right. So depth first. You start at 0, but well, yeah, you start at 0.
Well, I guess go through the list of what 0 is pointing to, and
Right.
well,
So
it has to be the smallest one.
So I'm pretty sure I talked about this first, but depth first is recursive. So depth first traversal,
Oh yeah, that's right.
visit 0, and bool visited. Those are where we've been before. So we need to create that. So bool visited sub mgraph.size. I forgot if C++ still allows this. Hold on.
Start is
There we go.
you're passing in a range.
Mm-hmm.
Pointers to
Let's see if I typed that correctly. Oh, almost. Visited sub I. So we initialize saying that we have not visited anyone. So this array is going to tell you if you visited a certain point or not. And what you're going to do is for int I equals 0, I is less than, again, mgraph sub size. Did it again with that parentheses. Incrementing I. we're going to depth first visiting I. All right, so we're going to start by trying to visit 0. The point of this is so we make sure everyone's visited at least once. Yes?
How is visited a pointer?
It's an array.
It's
If you use
always-
solid brackets, where does that mean the array resides?
Solid brackets?
Where is visited reside? What piece of memory?
Stance is pointers.
But this is a pointer. When you initialize it, it's not anything, it's a pointer.
Well, hold on. Let's stop. What is visited? What is visited's type? A Booleans. All arrays are actually pointers. But where does visited actually reside? Static, stack. Okay, so it resides on the stack. So you have to still jump to different parts of the array, which is why visited is actually a pointer, even though I'm using solid brackets. I could have used new, but I just did this way for convenience. All right, so here, depth first traversal. What is our base case?
If will equals visited.
Yeah, if it's been visited, get out. So if visited sub node, yeah, if it's true, then you just return. If it's not true, then that means we need to set visited sub node equal to true and go ahead and visit the node. Correct? And then we need to go for loop, going through all of its elements, trying to visit each thing it has. So let's go steal that function again. Bet you're glad we wrote this function. See, pair, iterator pair, not at start, but at node. And I should have copied the next line as well. You okay? Oh, yeah, a lot sniffy. Just make sure you're okay. And of course, we want to go, you're dying slowly. No. As well. And that's where we're going to do depth first traversal, passing in the visit function. And of course, I pair dash first, which is the destination, and passing along visited as well. And that should be it.
Why is the dash is the I pair pointer?
Yeah, because it is a, hold on. Let me see if I can answer this correctly. It is an iterator, which you are to treat as a pointer. They don't tell you it's a pointer, but you're supposed to treat it as a pointer. Just pretend it's a pointer. It may or may not be, but just pretend it's a pointer. All right, let's see what that does. Hey, look. Oh, good. So 0 to 3, that makes sense. 3 to, can't go to 0, goes to 6, that makes sense. And then 6 can't go anywhere, you pop it all the way back up. You go 1, 1 can go to 9, so it goes to 9. Can't go back to 1, so we go back to 2, can't do anything. 5, 6, we already did 6, so then 7, can't already been to 6 and 8. Perfect. So there's your depth first traversal. And I'll let y'all do breadth first. Yes?
Wait, do you go first to this slide?
Yeah, you do both.
But like, was it not in the function? In the CP?
It wasn't in the CPP, but it's in the HPP.
Okay.
Okay, let's see. Lastly, let me go ahead and stop this recording, and then we'll talk about Prim's algorithm because we need to go and go through that, and then that should conclude. I'm going to stop this recording and figure out what the also the answer to whether we need what to do when you try and add an edge that already exists.